I'm Fraser Campbell. I'm a PhD student here at Glasgow University.
Yeah, I'm Holly Campbell. I'm also a PhD student here at Glasgow.
Not related.
No.
We're basically this setup is to try and describe to people how gravitational waves work, and try and give people a feel for what space-time actually is and how it influences gravity, and then how masses like orbiting black holes colliding cause ripples in it that we can detect here.
And then we take people over here and we teach them how the actual interferometers at LIGO work, and we let them become the interferometer and measure a gravitational wave coming towards Earth. So that's what's going on here. I think we've managed to take the main concepts, and illustrate them in such a way that it becomes quite clear.
Yeah, we is making it as tactile as possible so that people get like a good visual representation, so it kind of sticks in your head, and then boiling down what is quite a complex setup into making some measurements on some rulers, and then using a laser measure to illustrate the fact that lasers are more accurate and they're faster at reading changes in distance.
Gravitational waves allow a new way to see the universe, to study the universe phenomena that's going on. Because currently we use different wavelengths of light, infrared, visible, but unfortunately it can be obstructed by matter, so you can't see things, or has to bend round objects.
Yeah.
Whereas gravitational waves don't interact that way, they just pass straight through, distorting space-time. So they allow you to study things that light can't.
So we're trying to explain gravitational waves today. And the idea is everyone thinks space is empty, apart from maybe stars and planets, but that's not the case. Today we're going to try and show you that space has a substance, okay? So if I put this object in, it could be any planetary object, the sun, let's say, when it goes into space, it actually has effect on space around it. If you bob it up and down, like some systems do, you can see that space itself moves. There's actually ripples. So like a stone going into water, you can see ripples coming out of it. If you even in fact twist the object, because it's kind of viscous space-time, there's actually twisting of space as well around it. Maybe we should have a bit more stars in there as well. You can see the effect.
I think the battery's dying.
Just put some stars into space-time. Okay. So far from the object, this object is still having an effect on space-time itself. When it moves up and down, you have waves as well, and that's what gravitational waves are. In Glasgow University, we're at the main forefront of the UK's contribution to discovering gravitational waves. They're very, very small, but when they go through us, we have now basically the detectors in place that we can see these small ripples in space-time. In September last year, in 2015, we were able to discover gravitational waves for the very first time, which is really cool.
It's really good to get people engaged in it, and to get people give them a better understanding of what actually happens. This is particularly good because it gives people a chance to figure out what actually goes on behind the scenes when you're making these complex measurements, and it strips back a lot of the complicated jargon and a lot of the complicated maths of it and boils it down to fractions on a whiteboard.